Our next speaker will be a keynote presentation by Wei Li from GM. So Wei's been doing some excellent emission control research there and been a great partner with us at Oak Ridge National Lab. And I got a cut me off. Apparently. Hello. Lights on. No. Hello. I said Oak Ridge National Lab and it broke. So I've had a chance to see a preview of some of Wei's slides, and I know there's some really good results in here. And so, some of them look very familiar. So please, everyone, continue to come in and take a seat. And Wei Li will lead us off with low temperature catalyst technologies, recent developments, and future needs. And appreciate you.
Thank you very much, Todd, for the kind introduction. And I do want to thank the organizers for the invitation, and thank GM for permission to present here today. Today I'm trying to give you an overview of low temperature emission control catalysts, highlight some of the recent developments, and also give you sort of my perspective from an industry researcher on some of the future research needs. As many of you know that low temperature catalysis is a very important area right now. That's mainly for two reasons. One is for the cold start. So when you start the engine before the catalyst becomes active, basically all the engine oil emissions will be untreated and flows directly out of the tailpipe. So as you can see here that, as you can see here that with the emission regulations in US for the next 10 years, we're going to see about 75% reduction of emissions. So basically what you will see is this line is going to continue to decrease, and that will require the catalyst to be active as early as possible. So you have to move this line to the left to reduce the time that basically the engine oil emissions will be untreated. So for that reason, the catalysts need to be much more active for the future. Another reason is globally there's a strong drive to reduce greenhouse gas on CO2s. I highlighted some of the countries here and areas that every region is basically looking for more reduction of greenhouse gas. And in particular, you will see that the three major markets for automotive vehicles, US, Europe, and China, for the next few years, they're going to have a significant reduction of CO2 required by, in this case, the fuel economy. So for that reason, all the OEMs globally are developing advanced engine technologies to improve the fuel efficiency of our vehicles. Some of the engine technology that we're developing includes downside boosted engine. So here you're going to have a turbocharger which is going to take some of the exhaust energy and push that back into the engine. And in addition, there's also Lindbergh engines that are being developed, and that also is going to drastically reduce the exhaust temperature. And the reason is actually very simple. As you increase the efficiency of the engine, you're using more of the energy for mechanical work. And that way, because of thermodynamics, you're going to have less energy in the exhaust for the catalyst. But that does pose a significant challenge for the after-treatment systems. In some of the examples I can give here, looking at one of the engines that we have, we're developing at GM, it's a Lindbergh gasoline engine. And here I'm plotting basically the engine speed and load, different conditions, and then looking at the exhaust temperature. as you can see here, that for many of the light load conditions, the exhaust temperature will be well below 200 degrees C, and especially after the turbocharger. So in those cases, the catalyst will face significant challenge to reduce the engine emissions. And obviously, there's engine management that we can work on to increase the exhaust temperature. However, that will be at a penalty of fuel economy. So with some simulation work that we did, we found that it takes about 3% fuel penalty in order to raise the exhaust temperature by 50 degrees. So in order to address this issue, the DOE and US Drive have worked together and developed established this goal that we want to achieve about 90% conversion of the emissions at temperatures about 150 degrees C. So this was done after a workshop back in 2012 with people from industry, academic, and national labs. And they identified the emission control technologies for low temperatures, focusing on low temperature oxidation catalysts, hydrocarbon and NOx low temperature storage catalysts, and also low temperature three-way catalysts. Along with this effort, we've also been working on developing a low temperature catalyst protocol that's going to include the reactor systems, sample preparation, test conditions, as well as aging and poisoning conditions. The idea is really trying to provide some guidance to the public in terms of how we should evaluate and prepare and age our catalysts, and hopefully harmonize our off-treatment catalyst development work with the engine development as well. And also really try to be able to compare results from different organizations and compare to some of the benchmarking catalysts. So for now, we have the protocols developed for our low temperature oxidation catalysts, for storage catalysts, and we're working on developing the protocol for three-way catalysts. The details of this can be found at the CLEAR's website, and that was given here. So we do encourage people to have a look at it, and if they can adopt some of the protocols, and if they have any comments, do let the CLEAR's team know that maybe we can work further improve the protocol. So then, the question becomes, so we know that low temperature catalysts are important, but how do we get to high activity at low temperatures? Obviously, we look for new materials. We look at promoters and really try to improve the intrinsic turnover frequency for each catalytic sites. That's one of the approach. The second approach would be to increase the number of active sites, and that can be by increasing the PGM loading as a sort of a very straightforward way. However, here I'm showing you a plot with different PGM loadings of a palladium aluminum catalyst. So this is palladium 20 grams per cubic feet, 80, 160, and 240. And as you can see here, that the light-off curve improves, so the light-off temperature decreases as you increase the PGM loading. However, as you further increase the PGM loading from 160 to 240, you don't see much improvement anymore. So at some point, at a high PGM loadings, your benefit is really limited in terms of further increasing the PGM loading. So therefore, I think the focus, a lot of recent work has been on how to improve the PGM dispersion so that improve the utilization of the PGM. And a large part of that effort is really looking at how to minimize the PGM sintering. And I'm going to talk a little bit a few examples about the approach to do that. Lastly, there's quite a bit of effort on looking at low temperature absorbers. both for hydrocarbon and NOx. There have been quite a few talks today already on NOx absorbers. So when you don't have the activity at certain temperatures, so the idea is if you can absorb at low temperature and as you warm it up, then the catalyst will become active and then you release whatever being absorbed, whether it's hydrocarbon or NOx for the conversion. So here's an example of some of the work being done at one of the national labs here. So PGM catalysts, as many of you know, are very expensive. So people have been looking at alternative materials. In this case, they were looking at mixed oxides, and there have been quite extensive effort in that area. I just highlight a couple of examples from their work. So when you look at the material is copper, cobalt, and ceria oxide. It was quite active for CO oxidation, but not so active for hydrocarbon oxidation. However, what they found was if you combine that with the platinum material, the platinum alumina, if you can combine the two, you get some kind of synergistic effect. This potentially could be because this catalyst is somewhat different from a PGM catalyst, that its CO oxidation activity is not affected by the presence of hydrocarbon. So potentially, it will allow you to remove the CO first and then enhance the activity for hydrocarbon oxidation. As many of you know that CO is an inhibitor for PGM catalyst for hydrocarbon oxidation. One of the concerns for any kind of a mixed oxide material, the base metal materials, is really the sulfur poisoning. And they did a very nice study here looking at the effect of sulfur, and not surprisingly, by itself, the catalyst deactivates very quickly with exposure to sulfur. However, by combining this with a platinum alumina catalyst, they found that the tolerance to sulfur was much improved. And recently, their group also collaborating with another group looking at some new materials. In this case, with manganese ceria as well as tin manganese ceria. So they show some interesting properties, and in most cases, is by combining a PGM catalyst with a mixed oxide catalyst. But again, like I mentioned, the key for those materials is really looking at the thermal durability and their sulfur tolerance. So those are the key challenges for mixed oxide materials. Before I get into quite a bit of discussion on aging and PGM sintering, I do want to demonstrate pick some of the case here that looking at a PGM sintering case. So for this catalyst, starting from a fresh catalyst, and then you age at different temperatures. As you can see here, the dispersion drops quite significantly as you raise the aging temperature. In this case, when you get to 900 degrees C, the dispersion is less than 1%, which means up to 99% of PGM that we put into the catalyst is actually not, and it's wasted. So obviously, that is a significant issue for all the automakers. The problem with that is the catalyst is inherently exposed to high temperature exhaust conditions. So for diesel, typically it's about 700 to 800 degrees C at the high load conditions. And for gasoline, it would be even higher and can go up to about 1,000 degrees C. So under those conditions, how do we minimize the PGM sintering is a significant challenge. Some of the approaches that people have tried, looking at different promoters and try to enhance the metal support interaction. So recently, there's also quite a bit of work looking at the coating, different material coating, including some of the atomic layer deposition technique. So the idea is really trying to see if we can modify the local environment of PGM to somehow minimize their sintering. So some of the examples I'm going to talk about, one of the very interesting work recently published was they were looking at, if you look at the platinum aluminum by itself, once you get to 800 degrees C, it sinters into large particles. And along with that, you will see the activity will deteriorate. However, if you just mix that with ceria, and you will see that they can somehow minimize the aging, minimize the sintering of the platinum, and you will see some of the platinum particles actually deposited onto ceria. And by using different ceria materials, morphology, so in this case, like ceria rod materials and polyhedral materials, and they were actually able to deposit all the platinum onto the ceria and not seeing any kind of sintering. So they also found that with that, you see enhanced activity for CO converging for this case. But this potentially could be one of the techniques that you can use to make highly dispersed catalysts. In this case, I think they did some very nice characterization work and found that a lot of platinum actually end up being single atom sites. So this could be a very interesting way to look at different, not only like to minimize sintering, but also maybe to make a single site catalyst, single site atom catalyst. Another work was done actually by Ming in our group. So he was looking at using barium in this case. I think they did looking at you adding the alkaline and alkaline earths oxides and use that to modify the platinum alumina catalyst. And he found that by looking at the promoted barium catalyst, he was able to get full dispersion. So it's all single atom dispersed catalyst even after hydrothermal aging at a temperature up to about 650 degrees C. And he's going to talk about that work this afternoon, 3:40. So if you get a chance, you can learn more details about that work. Another very interesting sort of development recently is so-called the Causal structure catalyst. So in this case, this example is we're looking at a palladium core and ceria shell unit. So they prepare some solution and having this very well-defined particles with palladium in the middle and ceria as a shell. And when they compare that catalyst to a conventional palladium on ceria and alumina catalyst, they found a much higher activity and also much better durability. So some of the things that I think they were thinking about, the reason for this is because when you have this interface between the palladium and ceria, really leads to much improved interaction between the metal and support. But I think a lot of work needs to be done to really better understand the mechanism for this enhanced activity. And also, they found that those cores are well isolated even at temperatures, heat up to temperatures at 850 degrees C. So it's much more improved durability as well. Another interesting sort of a similar approach is a Causal structure on Zirconia silica. So in this case, inside you have a core of silica, and on top of that you deposit a thin layer of zirconia, and then the palladium was exclusively deposited onto the outside surface, so it's only on the shell. And when you look at that catalyst versus simply a palladium on zirconia catalyst, you see again improved activity and durability. So this is quite interesting because obviously, if your palladium is only interacting with zirconia, you would think that the inside shell should not be making too much difference. But the data tells us that there is interaction even beyond just the direct interaction to the shell. So there's quite a bit of understanding, I think, we can learn from this kind of work that hopefully will help us further design a local structure to further optimize the activity. Some other interesting development looking at some of the core shell structures. In this case, they're looking at a palladium core, a platinum core, and a silica, and also found a very much more improved stability in this case. And for this one in particular, was the one on the right in particular was quite interesting. Is they fixed the size of the core, but varying the thickness of the shell. So in this case, they were looking at different size of shell, and indeed they actually found different performance, different activities for those catalysts. So that's another way of you can actually have quite a bit of control over the local structure of, in this case, the platinum on Syria. So by changing a lot of those parameters, hopefully we can understand better of the interaction between the support. In this case, it's more of the shell and the PGM particle in the middle. The question that obviously we ask is, and right now we don't know, is can this kind of structure really survive in the harsh environment of vehicle exhaust? So it'll be interesting to see when you expose those kind of materials to the aging conditions that we typically use for realistic aging, how they will behave. I think that will be very interesting. Finally, I want to mention there's some recent work looking at a similar kind of coating idea, but using the technique of atomic layer deposition. So for these examples, they prepared a palladium alumina catalyst, but then on top of that, they deposit about 8 nanometers of aluminum overcoat. And interestingly, they found that there are some mesopores or micropores that allows the gas to actually diffuse into the catalyst. So the gas will still have direct access to the PGM site. So you can vary the depth of this and make sure that the catalyst is still available. And so that's one of the approaches that you can take. And the other one is they use a palladium serial catalyst. They use ALD to deposit thin layers of zirconia. What they found was, again, it helps to stabilize the surface area of Syria, improve the catalyst thermal durability, and also improve the sulfur tolerance. In this case, you can see that with this coated catalyst, after different temperature heat treatment, the activity changed very little compared to the uncoated catalyst. So that's try to sort of summarize some of the interesting work been going on to minimize this PGM sintering. Now I'm going to switch gear and talk a little bit about absorbers. So this is looking at some of the hydrocarbon absorbers. This concept has been proposed for some time now, and typically when you look at a conventional three-way catalyst, compared to a hydrocarbon absorber, typically you will have additional layers of zeolite materials to absorb hydrocarbons. And what you would like to do is to store hydrocarbons during cold start and then release them at higher temperatures once the catalyst becomes active. And obviously, with any of the catalysts that you use on vehicles, you need to have good thermal durability. So when you look at the function of absorber, so if you look at the inlet hydrocarbon, when you start absorbing, you at a low temperature you will absorb the hydrocarbon, but as you raise the temperature, the hydrocarbons will start to release. So ideally, you would like once they start release, the catalyst will be active enough to convert all of those. But in reality, that's not the case. So as you release the hydrocarbons, the catalyst is not fully active, so you will only be able to oxidize only partial, only a small portion of the stored hydrocarbons. And this is very dependent on what kind of hydrocarbons you use. So I'm going to talk a little bit about the hydrocarbon species that we see in some of typical engine exhaust. You will see that it's fairly complicated, but you will have the shorter chain olefins like the C2 and to C3 or C6, and then a large fraction of C5 is isopentane, and also isooctane is another major component, and then plus some of the aromatics. So in order to really evaluate the performance of hydrocarbon absorbers, you need to make sure that you have a representative feed of hydrocarbons in your testing. So in this case, this is one of the works we did recently, and we're looking at a propylene, isooctane, metaxylene, isooctane, and isopentane. So we were looking at the storage of those species, as well as the desorption of those species and the oxidation of those species after different aging conditions. So as you can see here that as you increase the aging severity, so from 800 to 850 to 900, the release of those species, the releasing temperature shifts to lower temperature. And meanwhile, the oxidation efficiency also decreases. So as you age the catalyst, the release will be earlier, but the oxidation will be later, so that the gap is getting bigger, and that's the challenge, which is really what we face. And also, another interesting thing that you can see from this chart is, for example, when you look at the metaxylene, the absorption of metaxylene is almost 100% in all those cases, even after aging. However, after aging, you will see that because the PGM sintering in those catalysts, so the oxidation activity of that catalyst is deteriorated. Now, at the beginning, after 800 degrees C aging, you can oxidize 94% of the dissolved hydrocarbon, but after 900 degrees C, you can only oxidize 22% of the stored hydrocarbon. So you really need to improve both the storage functionality, try to hold on to those stored hydrocarbon a little bit longer, and at the same time, you also need to improve the oxidation functionality of this catalyst. When you look at the oxidations, we also found that overall, after 800 degrees C aging, we were able to oxidize about 45% of the total hydrocarbon. But when you raise the temperature to 850, it's less than 30% now. But if you go further to 900 degrees C, you can only oxidize about less than 10%. So again, it shows the impact of the aging of those catalysts is very severe. We also look at the palladium loading effect on those catalysts, and we found that it's, in some cases, the PGM loading is certainly helpful for one of the catalysts that we evaluated. However, the impact is not that significant for other catalysts, so really depends on the catalyst formulation. In this case, the impact of PGM is not that significant. So to summarize the work on hydrocarbon absorbers, what we found that it really depends on what kind of hydrocarbon species that you have. And for metaxylene or propylene, I think we have they work quite well, the hydrocarbon absorbers. We were able to control them to a certain degree. However, the alkanes, like the isooctane and isopentane, are very difficult to control using this technology. One of the reasons, because even if they store, they release well before the light-off temperature of the catalyst. So that's really the challenge. And also we found that at 900 degrees C aging, really destroys most of the functionality of the hydrocarbon absorbers. So interestingly, what we found was the zeolite structure was still there, and the total storage capacity was still intact. So the problem is they're releasing earlier and oxidizing later. So the gap between the two really is the challenge here. So now I'm going to talk a little bit about sort of how to combine those together to really work on a vehicle off-treatment system. So in this case, this will work from Johnson Matthey. They combine a new material they developed as a three-way catalyst by combining the serial zirconia deposited on alumina. They found improved performance because of the interaction between different species there. But they also combined the low temperature three-way catalyst with an on-the-floor extruded hydrocarbon absorber. So by combining those two technologies, they were able to reduce the tailpipe emissions quite significantly. Now I'm going to talk a little bit about NOx absorbers. It's a very interesting development recently, looking at the palladium exchange zeolites as a very efficient NO absorber at a near room temperature. So there's a work that recently did, they published this on palladium ZSM5, but also on some other palladium zeolite, you also see this effect. So the interesting thing is compared to the traditional NOx absorber is this technology does not require the conversion of NO to NO2. So you can actually absorb NO at close to room temperature. So when you combine the NOx absorption with hydrocarbon absorption and a diesel oxidation catalyst, you can really put together a sort of a multifunctional catalyst that will able to convert quite a bit of the cold start emissions. And when you combine that with SCIF catalyst, so that's where you put together the system level to really integrate the different functionalities. So in this case, the DCSC catalyst will absorb NOx, absorb hydrocarbon at cold start conditions. And then once the temperature raised above the releasing temperature, so the hydrocarbon would release as well as the NOx. And the NOx release will be converted by the urea injection on the SCR catalyst. So that's the concept of overall system level integration. And they have demonstrated also very recently that this technology has very good durability under lean conditions as well as sulfur tolerance. One of the issues they highlighted in their recent paper was that it does deactivate under rich conditions. So that's one of the challenges that we'll have to work on. Lastly, I just want to mention that when you look at a practical system, looking at try to achieve a low temperature, many times it's more than just one catalyst. It's a whole system approach. So here's the example that the work with Cummins and PL and Johnson Matthey. So in order to achieve a sustained low temperature NOx emission, NOx reduction in their region at over 90 degrees, 90% at 150 degrees C. They had to look at SCR formulation, DOC formulation, as well as the reductants. So in this case, they need to introduce gaseous ammonia. So in order to really combine the whole system level performance to achieve 90% conversion at 150 degrees C. So to summarize, I hope that I was able to convey to you that really we need quite a bit of research to address the low temperature emission control issue. And one of the critical issues I want to emphasize is the catalysts really need to be aged and tested under realistic conditions in order for us to have a proper evaluation of the potential of the catalyst. Some of the examples I give on the nanostructure PGM catalysts have shown some promise. However, I think we do need better understanding of the mechanism why those materials are working better, and hopefully will help us to further design improvement structure. Hydrocarbon absorbers, we need more thermally durable. In this case, we're looking at temperatures more than maybe 850 degrees C, and it's really more about the releasing temperature rather than the structure, because we can maintain the storage capacity. It's more about they're releasing too early, so that's one of the issues that need to be addressed. And some of the new concepts of multifunctional catalysts, like I mentioned, the CSC concept, but there's some durability challenges still remains. And finally, I just want to mention that in order to develop a practical system, many times you need the system level approach as well as just a catalyst. So with that, I'll conclude my talk, and thank you for your attention.
Thank you very much, Wei. Fantastic. The floor is open for questions. I'll start us off after Carlos.
So, especially on the gasoline side, fuel economy requirements are beginning to increase pretty substantially.
Yes.
Is this having any effect on the aging temperatures that the catalysts need to sustain as exhaust temperatures continue to cool?
So the question is about aging requirements for gasoline engines. Unfortunately, because of the downsizing of the engine displacement, many of the high load conditions, the load is actually going higher. So the aging conditions are actually going the opposite way. Although the exhaust, in most cases, exhaust temperature is going down, but the aging requirement is actually going up. So it's a significant challenge for all of us.
On that note, so the turbo downsize is definitely a path. What about some of the advanced combustion modes that could be sneaking in? Are you seeing that getting closer to reality, and which would, again, create a new area of emission control research, or do you see that far, far away?
So certainly I think some of the new technologies are quite interesting, quite promising. Some of the lean burn engines, you're probably aware that lean gasoline is, there's production lean gasoline engines, maybe not in the US, but in Europe. So a lot of those technologies people are all looking at. The question is really, sort of a system level balance, whether it's after treatment, whether it's engine itself, and the benefit, the fuel economy benefit compared to some of the stoichiometric engines. So it's hard to predict when there will be, broad implementation of some of the lean burn engines, but certainly I think we're all working towards that.
Time for one more question. All right. Well, we'll let you go. All right. Thanks a lot, Wayne.